Here we are.
Hello, my name is Kevin Kusabyan, and I've been the first use case lead in this project. I work as a research scientist in SINTEF Ocean in Trondheim. My main working area is modeling and simulation of maritime energy system and designing and testing of hybrid power system. In this use case, the main question we tried to answer was if co-simulation using OSP software is a useful tool for the system design in early stage. The question is, in short, can we or should we run a system simulation using OSP from day one? So we formulated the use case into a collaborative design study together with partners in the JIP. And the main goal of the design study is to find an optimal sizing of power system and battery ESS for hybrid ferry together with optimal control of the system. Our cost function is the total cost of ownership, ideally. Then why this use case? We wanted to explore the feasibility and benefit of the using OSP in the earlier design stage where you need to run a large number of simulations. And you need to also build a system model with components from different parties and apply models-based systems engineering and knowledge-based engineering. Before we get into the detail of the use case, let us answer some questions. Why do you need dynamic system simulation so early in the design stage? In the hybrid system, a battery or energy storage system unlocks the possibility of optimizing the design or operation by easing the requirements for the power balance between the consumers and producers. Peak shaving, load leveling, spinning reserve, and zero emission mode are such operations. A challenge is that these operations will not always save energy, but may be opposite. A proper control strategy with correctly sized machinery under specific operation profile will maximize the benefit of the novel technology. Here, system performance is of our key interest rather than the best performing components. In addition, we need to take into account the dynamic property of the components, primarily battery, to evaluate the system performance, when to charge or discharge, or how fast should we do it. All this combined will result in a better or worse performance. Let's take a look at a specific example. This plot comes from one of our simulations. Here you see that battery is responsible for the propulsion and auxiliary load in the beginning until the gensets are ready for providing power. In addition, there is a short power rush to accelerate the vessel, so peak shaving is happening. As the propulsion load is going down to a steady state, battery is charged in order to maintain its state of charge. When the state of charge is at the desired level, charging stops and all powers are supplied by gensets only. At the end of the journey, propulsion load drops and the vessel is on zero emission mode. There are lots of things happening in this short transit, and it will be very difficult to tell whether this type of operation will really save fuel and reduce emissions at reasonable capital cost without running the dynamic simulation. And ship design is an iterative process in which a small cycle of synthesis and evaluation of the system happens iteratively. In this process, designers and engineers gain a lot of knowledge about the nature of the system, better parameter sets than others, sensitivity of the system, and testing method. In our approach, we try to gather these knowledge into the system model rather than document and drawings. Also, process-related data are stored in the database. System model and simulation is not only a tool for evaluation, but also storage for the knowledge that can be passed down to stakeholders in later stage. Okay, final question. Why OSP then for early design stage? OSP as a co-simulation software provides a platform where we can create a system model in collaboration and without concern of breaching IPR. As we work with models on the platform, we can communicate our requirements, specifications, and interfaces through the models and get more tangible feedback and evaluation. Finally, as it is an open source software, it is up to the developer to customize a tool to the specific needs as we have done in our use case. Okay, let's look at our use case finally. We selected target vessel and system as shown here. It's a road ferry designed by Damen Shipyard. You see the schematic of single line diagram on the right. So we have two gensets, battery, and two motors. We teamed up with many among JAP partners. Corvus Energy, Damen Shipyard, DNVGL, Havyard, JMU, Monaco Technology Institute, and of course SINTEF and VAR's Shipyard, Ship Design. I'm very proud to lead that has quite a large number of participants. And each of partners contributed to the use case with model, knowledge, ideas, and interesting discussions. As a team, we defined our task as defining the system specification, developing a design tool, running system simulations, and thereby performing a design study. We spent some time together defining the system scope and structure, model fidelity, and interfaces. These were crucial steps before we go down into modeling activity. And I believe that this should happen in any activities before we really build system simulation. Then FMU models are actually developed by 5 participants and delivered to me so that the system can be configured. As we needed to run a large number of simulations, we mostly used the quasi-steady state models while maintaining a crucial dynamic property such as vessel motion, propulsion load changes, and power balance in the power system. The system simulation typically runs at 30-40 times faster than real time, which is ideal for the early design trials. This system model can be further elaborated further into in the later stage while keeping its structure to serve other needs such as design verification, hardware and load testing, and virtual commissioning. Another main task in the use case was to develop an integrated design tool that embraces the design processes with an intuitive UI and support for database. In order for a tool to be a collaborative tool, the tool is developed as a web application where many users can work simultaneously with the same source of FMU models or system models. Now we'll see the design tool in action. I'll show you a video of how it works in real life. Okay.
Yes, we can
Here's
hear you.
our design tool application. You can access it using a web browser by connecting to the UI server. It allows multiple users to access simultaneously to facilitate collaboration and to allow wider use in an organization. It has 4 core functionalities: FMU management, system configuration, simulation setup, and viewing the results. In FMU management, one can upload FMU files in the local PC to the server so that others can reuse the model or collaborate on a common project. Uploading is simple as shown. You may add additional information by putting memos or provide its category so that it can be easily identified during the system configuration. Here you see you can also add OSP interface as Severin introduced to an FMU. If you do so, the OSP interface can be reused in multiple system setting configuration or used by others also. Here is a short demo of creating a physical electric port interface, combining voltage and current. And we'll see how this is used in the system configuration. So after you identified all the FMUs that are necessary for the system, we can start configuring system. The design tool supports graphical user interface for the system configuration, and process is simple and intuitive. First, you will drag and drop the FMU from the left pane to the editor section, our component. And then you rename our component so that it can be easily identified. Necessary interfaces or ports are selected and added to the component. Inputs port on the left, outputs on the right. A physical port, which can be either input and output, can be shown on the both sides. Then we can simply connect the ports. The editor will not allow illegal connection between the incompatible ports. Here is the complete system for our use case. We have used functions to convert the signal from RPM to radian per second. This will greatly help when you have conflict in units between two components to connect. We used OSP interface for the system for the physical connections such as shaft electric connections and variable group connection for multiple signals going from PMS to other components. This reduced number of connections from 41 to 29. And it also helps to preserve the structure of the model similar to its conceptual one. And this greatly helped communication between collaborators through models. Now we can start the run simulation. This is the fun part. We can simply run and check out the system behavior, which looks a bit boring because it lacks the operation profile. So we added a scenario that reflects vessel's operation profile using the GUI, graphical user interface in the tool. In addition, you'd like to explore how different design parameters will affect the system performance, fuel consumption in our case. We can use different design of experiment method to populate a large number of sets of key design variables. When these are configured, we can start simulation at batch. Actual simulation happens in the remote CoSim server and will notify the user when the simulation is done. We can check the time series output to see if the simulation makes a useful or sensible result. Then the tool will also summarize finally the time series output from the CoSim to more interesting values such as fuel consumption, running hours, and others for each case. We're seeing the result of summary of 100 cases in the design study. Here we can easily sort the table to see which combination of sizing and control parameters have given the least fuel consumption with an acceptable drop of state of charge. The table can be also exported to run more thorough analysis or plotting. A possible further step is to build a surrogate model from these outputs and optimize the system parameters. So this is the end of the demonstration of the design tool. Yeah. So this is my final slide in my presentation. And I like to revisit the value of OSP in our use case in design phase. So collaborative work is important, especially in the early stage, because there are lots of things we have to determine together. What's the model fidelity we should start with? And what will be the motor interface that will create the structure of the system? So we had quite enhanced experience for building a system model using OSP. As Severin introduced, Levy introduced, it was simple and secure model sharing. And we didn't need a special simulation tool for multi-domain simulation. and simplified interface makes system modeling easier. And as you have just seen in this customized integrate design tool, it is quite easy to integrate into custom software using this open source software. Okay, there's not only positive part of the story, there's also a bit struggle. Debugging of the system model is very challenging. Once you get the black box model, which are not very well documented, then we have frustration, as Severin introduced. So I think we need a bit more rigid or robust framework for testing and documenting model, and that will be further developed in our open source environment, I hope. As a concluding remark, this design tool that we made is not open source, but the core, the functionality is made as an open source Python package to run code simulation in Python environment. So if you are interested in developing your software in Python environment using code simulation, then you are free to use this open source Python package. Okay, this is the end of my presentation. I'd like to thank you for listening to my presentation, and also thanks to all the enthusiastic participants in our use case team. And I'll give my words over to Thomas.